greetings from me. My name is Vasileios Tsiolakis. In this presentation, we'll follow a bit of a different approach. We have open problems, yes, but we will focus more on the concept that brought forth our group. And my job is to introduce our group to you. It is the Advanced Model Reduction, or AdMoRe group, a Marie Sklodowska-Curie ITN funded by the European Union. And it consists of 8 PhD students: Guillem Barroso, myself, Simona Vermiglio, and our postdoc, Matteo Giacomini. The title of this presentation basically sums up what we want to do: empower decision-making in simulation-based engineering, advanced model reduction for real-time, inverse, and optimization in industrial problems. And how this came to be: basically, our industrial partners, Airbus, Volkswagen AG, Siemens Healthineers, and ESI had a list of open problems, and the academic institutions, Universitat Politècnica de Catalunya, Swansea University, and École Centrale de Nantes, in collaboration with the industrial partners, said, okay, if we use our new methodologies and techniques, we're pretty sure we can bring forth a solution. Now, computer-aided engineering, we all know it's an integral part of any industry. But the issue right now is that conventional methodologies have very distinctive steps. Basically, if you want to study any phenomenon, you have to go through a pre-processing step, which could be 3D modeling, could be mesh generation, just deciding what the characteristics of an experiment is, basically. Then you have to plug this into a solver, run your code, get some results. And finally, you need to do some post-processing so that these results are something that you can actually use. And the thing is, each step of this is expensive, and the connection between them is also quite time-consuming. And that means that it is very incompatible with real-time processes, real-time methodologies. And this is what we aim to do: basically create physics-based tools for real-time processing. On the one hand, we would like to be able to make decisions in real time, good decisions, taking into consideration one example: in the manufacturing processes, a good part and a destroyed part is just fractions of a second away. And it would be very nice to be able to have a tool that will be able to control this process faster than that. We would reduce the costs, and we would bring the production phase and the designing phase much closer together. And on the other hand, we would like to be able to do, in an efficient and quick way, optimization, multi-parameter optimization, do parameter identification for considering uncertainty, quantifications, and basically, at the end of the day, be able to solve many parametric problems that we wouldn't even consider to solve if we were using the conventional methodology. And because an example is always better, let me introduce to you, it's a very common problem, the microswimmers, basically. We have a parameterized Stokes flow around 2 cylinders, and we are introducing 2 parameters. The first parameter controls the inverse of the distance between these 2 swimmers, the cylinders, and the second parameter controls the radius of the left cylinder. And we also have a constraint that the surface area, the global surface area of these 2 cylinders must be constant. So, basically, okay, here you can see we are visualizing the solution. Okay, we have pressure and the streamlines and velocities, but the important part is right down here, the sliders. Right? You can see that as we move the slider, we are basically changing completely the problem. And the important thing is that we are getting a representation of our new solution in real time. So basically, we can play with these parameters each time, and we will be doing, let's say, real-time design, interactive design of these microswimmers. Okay. And now, Guillem Barroso will continue to be a bit more exact on what our problems are.
Thank you very much. Good. So thanks for the introduction. Now I'm going to present the AdMoRe network, which is being introduced for Vasileios. And I'm going to talk about the 4 actual problems that are presented for one of each companies. Again, Airbus, Volkswagen, Siemens, and ESI. And we're working in collaboration again with Swansea University, Universitat Politècnica de Catalunya, and École Centrale de Nantes. So, first of all, those are the 4 projects that we are solving. One related to composites and forming technology, one related to fast simulations for geometrical design, then inverse problems and identification, and integration of reduced order models into commercial software. So at the end, we want the industry to use our tools. So that is a key point as well. So first of all, the first project is in collaboration with Airbus, and it's real-time monitoring and controlling of composites production. In the case, we have always the experiments that we saw in order to calibrate our models. The problem is that experiments can be really, really expensive, and the models might be not that accurate. Also, we have a stage of design and optimization, which is pretty expensive with the traditional tools that industry uses right now. And as Vasileios was saying, it's going to be really, really nice to have a control and monitoring our process. The problem with this is that we need a real-time simulation in order to control the process, and we cannot do that right now. So what we're using is, again, these experiments to extract information of our process, calibrate our models, and then for the design and optimization stage, we're going to apply reduced order methods in order to, for example, smart techniques, for example, the DGD, in order to consider parameters in our solution, and then in order to optimize and speed up this process, and then achieving real-time control and being able to monitor our solution. That was for Airbus. Then, for example, for Volkswagen, we have interactive shape design and real-time aerodynamics optimization. In their case, they have 3 main stages in the design. One is static constraints. So you design the car for the designing department. Then you have your model that the designers are happy with, and you bring it to the mesh generation. There is a whole new department that they generate the mesh. And then you give it to the CFD guys, and they compute the solution. The problem is already 2. We have 3 stages, and we have lots of iterations. Of course, you're not going to like your CFD results. You're going to go again to the design process, and you start the chain. That's one problem, large number of iterations, meaning high computational cost. And the second problem is that is Volkswagen. So thousands and thousands and thousands of engineers. Those are different departments. The connections are not that easy. So what are we going to try to do is design tools that can be used as a black box. For example, what Vasileios was showing before, moving sliders that the designers can actually see the CFD results in real time while they are designing the car, and see if what they are doing has an effect on the solution, drag, lift coefficient, and so on. In order to do that, we use 2 approaches, a low-order approach, because it's what industry uses, and it might be clearly enough to compute the solution. And then also high-order approaches when we need, when we have really difficult flows, and then we need to be highly accurate. That was for Volkswagen. Then the Siemens case, we're interested in the fast design and high-fidelity benchmarking of MRI scanners. I guess you all know how an MRI scanner looks like. This thing here makes a lot of noise. And it's widely used because it's not intrusive, and it has a high performance in soft tissue, tumor detection, and so on. And we have a complex couple problem inside the MRI scanners, which this is like a summary. We have conductive components in between, and then a couple problem in between electromagnetics, mechanics, and acoustics. And well, this is a hard problem to compute. And also, here in this project we have 2 lines of work. One is a bit related to the car that I was explaining in Volkswagen. We have a design stage of those MRI scanners, in which you want to play with geometrical parameters, material parameters, and then this means that you have to do all this process of designing, setting the parameters, generating the mesh, designing, post-process the results, and go over and over. And it's indeed high computational cost. And we're going to try to apply, for example, in this case, the PGD in order to speed up this process. And then once we have an MRI configuration that we're happy with, we'd like to go and verify and validate this problem. That is done through a fully coupled 3D solver, which the focus is not on speed, but in highly accurate results. So that's it for Siemens. And the last one comes from ESI, and they're interested in data-driven validation and verification of reduced data models in commercial codes. So trying to actually bring these new technologies to the commercial source, because otherwise the industry is not going to use it. So in this case, again, 2 lines of work. One is related to composite microwave heating process, in which we have generated models and different layers of materials. So we have huge gradients, and we really want it to be accurate in the thickness of the solution. And then the other one is automotive car radars. And I guess here we all agree that we need real-time response for identifying which object we have in front of us. So for the composite microwave heating, the approach is to break down the 3D model in a 2-dimensional in this let's say big area, and then a 1-dimensional in thickness, so we can refine a lot our mesh and be really accurate along the thickness. That's called in-plane, out-plane decomposition. And then for the automotive car radar, we're going to use high frequency wavelength in order to identify our objects. So mainly we need to know what do we have, where is it, and where is it going. So yeah, that's what we are trying to do with ESI. So those are the 4 key points of all these projects. We really need to compute parameterized solutions in an accurate way. So we can bring, for example, material and geometrical parameters into the solution. Then being able to take real-time decisions, that is going to be key for almost all the projects. Then data-driven verification and validation, and from knowledge to code, meaning that we have to implement those things as packages for commercial software in order to be used for industry, because otherwise it's just not going to happen. From these 4 points, we can develop these 2 consequences, which is going to be being able to implement these in the daily production environment. So, for example, with the Volkswagen project, having this tool that you can see the CFD results in real time while you're making these changes in the design of the car. And then, for example, generate end-user apps for smartphones. They can go to a meeting and check whether the thickness of this conducting shield in MRI scanners is better or whatever. And then at the end, what we're going to achieve is fast and smart designs, and then the ability to try some unlikely ideas that otherwise we wouldn't have time to invest or even money to do so. So that's it for me. Thank you very much.